Okay, so let's talk about one of the biggest ideas in cosmology, cosmic inflation. It's our best guess for what happened in the very first sliver of a second of our universe's existence. But here's the thing. The standard story has a few, well, major holes in it, and it turns out the solution might be hiding in the problem itself.
So the whole mystery really boils down to this one question. Why is our universe so perfect? I mean, when you look out at the biggest scales imaginable, everything is incredibly smooth, uniform, and almost perfectly flat. It's neat, tidy, and that's a huge problem because, honestly, the Big Bang Theory, on its own, predicts the exact opposite.
Yeah, if you just let the Big Bang happen without anything else, you'd expect a total mess. A lumpy, bumpy, chaotic universe all twisted up. But when we look at the afterglow of the Big Bang, the cosmic microwave background, it's just smooth, astonishingly smooth. It's like something came along and steamrolled the entire cosmos flat. So what gives? What could possibly do that?
Well, the leading contender, by far, is this idea called cosmic inflation. The theory goes that in the tiniest fraction of a second after the Big Bang, the universe went through this period of absolutely insane exponential expansion. We're talking mind-bogglingly fast. It basically took one microscopic, messy patch of space and stretched it out so huge and so fast that all those wrinkles and bumps were just ironed out flat. And that's the universe we live in today.
It's a really neat idea, right? But, and this is a big but, the standard story of inflation comes with some really big question marks. These aren't just little details. They point to something fundamentally missing in our picture of the early universe. Let's get into it.
Okay, so at the heart of the standard theory, there's this thing, a hypothetical particle field that physicists have dubbed the inflaton. This is supposed to be our culprit. The idea is that it just popped into existence, flooded the baby universe with this kind of anti-gravity energy, and boom, drove that insane expansion. It's the engine.
But here's the problem. Problem number one, we've never ever seen it. It's a complete ghost. Problem number two, for it to work, its properties have to be tweaked just so. I mean, it's incredibly fine-tuned. And the biggest problem of all? We have no earthly idea where it came from or what it is. We basically invented a mystery to solve a mystery.
And this is the real kicker. For you and me to be here, for stars and galaxies to exist, inflation had to stop. That inflaton field needed to decay and dump all its energy into creating the stuff of our universe. But the standard theory gives us no good way to make it stop. It's like a cosmic car with the gas pedal jammed to the floor. There's no brake. How do you ever turn this thing off?
And this is a huge clue. The fact that we have to invent this thing out of thin air and then can't figure out how to turn it off, well, it suggests we're not just missing a piece of the puzzle. We might be looking at the puzzle all wrong. Maybe the answer isn't a particle at all. Maybe it's something about geometry.
And this is where things get really, really weird. If you can't reliably turn inflation off, quantum physics says it just keeps going, forever. Not everywhere, but in patches. So you get this runaway process called eternal inflation, creating an infinite churning sea of new universes, a cosmic foam of bubbles. And our entire universe would just be one tiny, lucky bubble where inflation happened to stop. It's a crazy idea, and it makes our existence seem like a total fluke.
Okay, but what if there's a totally different way to look at this? A new model, called the Conformal Emergent Reality Model, or CRM for short, flips the whole problem on its head. It says, hey, maybe the problem isn't the engine we invented for inflation. Maybe the problem is how we think about the racetrack itself. You know, space-time.
So the core idea of CERM is pretty wild. It suggests that space-time, the fabric of reality, isn't the most fundamental thing there is. Instead, it emerges from something deeper, a kind of primordial geometric code. Think about it like this. The wetness of water isn't a property of a single H2O molecule. It's an emergent property of all of them working together. CERM says spacetime is like that.
And that changes everything. Because if that's true, you don't need to invent some mysterious new particle, some inflaton, and just drop it into the early universe. The solution isn't some extra ingredient you have to add. It's baked right into the recipe for spacetime from the very beginning. So if we toss out the inflaton, what's our new engine? Well, meet the omegon. And this is the crucial difference. The omegon isn't some particle living in spacetime. It's a vibration of spacetime's underlying geometry. It's not a boat on the ocean. It's the wave itself. And here's the game-changing part. The Omegon has a property unlike anything else we know of in physics. Its mass isn't constant. It's not some fixed number. Instead, its mass changes depending on the geometry of the space it's in. Specifically, it's directly tied to the curvature of spacetime.
This is it. This is the whole secret sauce right here. Mass is proportional to curvature. That's the rule. So if you're in a place with a lot of curvature, where spacetime is all twisted up, the Omegon is super, super heavy. But if you're in a place that's really flat, the Omegon is incredibly light. Everything else follows from this one simple idea.
So let's put that into perspective. In the fiery chaos of the brand new universe, space-time was unbelievably curved. So the Omegon would have been crushingly heavy. But today, in our big, old, stretched out, nearly flat universe, the Omegon would be so light it's practically massless, a ghostly whisper of its former self.
Okay, so you can probably see where this is going, right? How does this idea of a changing mass give us the off switch for inflation that we've been looking for? Well, this is the really beautiful part. It's not something you have to force, it just happens, all on its own.
All right, let's play this out. Step 1. In the very beginning, the universe is a tiny, intensely curved nugget of space-time. This makes the Omegon super heavy, and its massive energy kicks inflation into gear. Step 2. The universe starts expanding like crazy. Now here's the magic. Just like expanding space stretches out light waves, that's redshift, it also stretches out the curvature itself. The universe gets flatter as it gets bigger. Step 3. As the curvature drops, the Omegon's mass plummets right along with it. Finally, step 4. The Omegon gets so light that it can no longer power inflation. The engine just sputters out. It stops. And all that leftover energy gets dumped back into the universe, creating the hot, dense state we call the Big Bang.
You see, the expansion is its own kill switch. It's a beautiful, self-regulating system. The very process of inflation sows the seeds of its own demise. You don't need any fine-tuning, no magic numbers, no mysterious stop signal. It's all just a natural consequence of the geometry.
So let's put them side by side. The inflation, where does it come from? We have no idea. What starts it? Some magical, fine-tuned conditions. How does it stop? Well, we don't know, it just does. Now look at the Omegon. Where does it come from? Space-time geometry. What starts it? The natural high curvature of the early universe. How does it stop? The expansion automatically makes it stop. One is a list of mysteries, the other is a list of answers.
What this really means is that inflation stops being this weird, bolted-on idea we need to fix the Big Bang. Instead, it becomes a natural, even necessary part of the universe's life story. And get this, the theory suggests that the leftover ultralight Omegons today could actually be the source of dark matter, so you potentially solve two of the biggest mysteries in cosmology with one single, elegant idea.
So there's one thing to take away from all this, it's this. Cosmic inflation might not be some external mystery we have to solve. The problem might actually be the solution. It's a self-solving puzzle, a built-in, self-correcting feature of space-time itself.
And that just leaves you wondering, right? If the answer to inflation is woven into the very geometry of reality, what else is hiding in there? Are dark energy and dark matter also just features of space-time's rulebook? Is the arrow of time itself in there somewhere? It really makes you think. Maybe the biggest cosmic mysteries don't need new particles or forces, but just a deeper understanding of the stage on which it all plays out.